Expected value, variance, and standard deviation. When we worked with discrete uniform distributions, the expected value was calculated using the expectation of x was the sum over all values of x, or at least all values of x where the probability was non-zero, of x times the probability that x is equal to x. And remember, typically x was integer values. Clearly, what we have now is a continuum, and we know that integration is the result of a sum over a continuum. So the analogue for a continuous distribution is that the expectation of x is the integral from negative infinity to infinity of x times f of x dx. In practice, of course, if we only have p of x non-zero in a particular interval, and we've met PDFs before, then we would have x times p of x between those values. Also, if the PDF is piecewise, as in the examples of the last section, then this integral is done piecewise, as we will see in the examples that follow. The variance can be calculated using Varx is the expectation of x squared, take away the expectation of x squared, just as with a discrete distribution. In this case, the expectation of x squared is the integral from negative infinity to infinity of x squared times f of x dx. And of course, that also has a direct analogue to the way it was calculated for a discrete distribution. Alternatively, we can use Varx is the integral from negative infinity to infinity of f of x times x minus mu all squared, where mu is the expectation. But I don't recommend this. I recommend doing it this way. As usual, the standard deviation is the square root of the variance. Note, and we've already alluded to this, the expectation being the integral from negative infinity to infinity of x f of x dx is the same as the integral below, as f of x is non-zero on the domain a to b. So the expectation of x would be the integral from a to b of x times p of x dx. P of x being the part of f of x where the probability density is non-zero.